This is Stephanie Washer, and this is section 4.1e through G, and we're going to talk about ARP, Address Resolution Protocol, Neighbor Discovery Protocol, and Ethernet. And this is for the Module 4 in the Network Plus Guide to Networks from Cengage and RBC's PCT 110 course this spring. So our Address Resolution Protocol, we're going to talk about it in relation to IPv4 networks. I'll touch IPv6 networks, but we really don't use ARP for that. And we're all at the data link layer. So these three protocols are all at the data link layer. So Address Resolution Protocol, all it is used to discover a MAC address for an IP address on your local area network. So our computers and switches want to know IP and MAC mapping. And ARP is the protocol that works with IPv4 in order to get those MAC addresses. And it's only within the local area network. It doesn't go beyond the router. And because ARP just broadcasts everything out, and it'll broadcast out, hey, do you have a MAC address for this IP address? And that's what they do. Just sends it out, and then whoever has that information will send a reply so that the computer can put it in their ARP table. And I'm going to go, if we go into ARP, I'm just going to hit ARP so you can see all of the different, so we've got ARP-A, which displays everything, so I can do ARP-A. That displays all of my ARP. And I've got multiple different IP addresses, and I can tell you, I believe this one is my actual physical address. This one's the one on my network. So, and that one I've got my router. You can see my router MAC address. So the other reason why I did the ARP, just basic ARP, you can see all of the different commands you can use with ARP. -G is just the same thing. -V, we can get more information over verbose mode. -D is to delete specific items in your list. If you use *-D and then star, it will delete all your hosts. Sometimes you have to just delete the ARP table and start over, and then -S to put in a static. So we've got static or dynamic addressing. So it looks just like this. And our dynamic ARP table entries are just when we send out an ARP message, or when a computer sends out an ARP message and says, hey, do you have a MAC address for this IP? It will automatically put it in its table once someone replies, and that's the dynamic entry. Static means we put it in there manually. And so the ARP utility put it in there manually, and it's just a way of obtaining information and manipulating a device's ARP table, so we can set that up. And then you can see here we've got they show you the ARP table. I probably should have not shown you my MAC address. I can go in and the ARP command can be used on IPv4 devices to diagnose and repair problems with the ARP. So that's what I was talking about, ARP-D and ARP-S for static. And then we have Neighbor Discovery Protocol. And that Neighbor Discovery Protocol is just a protocol used by routers and other devices to learn information on the network. So IPv4 uses ARP and ICMP, while IPv6 uses the Neighbor Discovery Protocol. So that's why we go through both of these. ARP is what's used by IPv4, NDP is what's used by IPv6. And NDP, so IPv6 has benefits above IPv4. NDP eliminates the need for ARP because ARP has a couple issues, and they're more resistant to, NDP is more resistant to hacking than ARP. And with NDP, we talked earlier about Slack and how that is managed and the different advertisements for it. So as a router, for network prefix and network table discovery, there are different tasks that are performed. We have router advertisements, where a router will send a message out to each of its interfaces, just kind of having all of its information, like the network prefix, the MTU, and the hop limit. And then a router solicitation is just waiting for the next scheduled RA message. Newly connected IPv6 host can send an RS message to request information from the router right away. Redirect, all it's doing is saying, we've got a better way to go out to the outside world, so a better gateway. The neighbor solicitation is just a message to request a MAC address of a neighboring mode. The MAC address is also called link layer address in IPv6. These messages are just so that no two devices are using the same IPv6 address. And then we have the neighbor advertisement, and that's just a response to the NS message. And finally, we have Ethernet. So this is the most important standard. It's what everyone uses. It's capable of running tons of different media on it. Very, very reliable, very reasonable. Okay, so it's all at the data link layer. There's so many advantages of Ethernet. We now have Ethernet 2 as the standard. It was developed back in the day by DEC, Intel, and Xerox before IEEE came about, or standardizes things. So some of the Ethernet standards are, and some of these are the older standards such as 802.3, and it can be used, we talk about these standards, but there's backwards compatibility, and it just depends on whether it's wireless or wired, and so we've got a bunch of different standards. We'll talk about those later, but the Ethernet standards add more fields to the header to give a little bit more control, kind of like similar to establishing that session in TCP. So in Ethernet, we break up that data link layer in between the LLC, or the logical link control sublayer, and the MAC sublayer. So the LLC is the portion that connects to layer 3, and the MAC sublayer is the portion that connects to the physical layer. So it's lower level, upper level portion. So the upper level portion, all it is it identifies the type of message and handles multiplexing, flow control, reliability, error control. And then the MAC sublayer puts that destination and source address on, and remember it's a MAC address, puts it on, includes the message, provides that checksum, and frames the trailer. So it adds both a header and a trailer because it's going to the physical layer to go across the network. So we've got the preamble, destination, source, Ethernet type, the data plus the padding, and then the frame check sequence. So here we've got it all here. And remember, destination source is MAC address. And then I just want to open this up a little bit. That frame check sequence just ensures the data at the destination exactly matches the data issued. And so it does this, it uses the CRC, or cyclical redundancy check algorithm, for the frame check sequence. And then there's a couple things just to remember for this information. The preamble and SFD fields are not included when calculating the frame size, so Wireshark can't capture those first two fields. And sometimes Wireshark can't even see the FCS. It can capture quite a bit, but not everything, but it can capture your MAC addresses. So, and then the header and the FCS make up the 18-byte frame around the data. The maximum transmission unit is the largest in bytes that the router, that it can send, that the router will allow. And so it defines that at the layer 2 frame. But there's always exceptions, right? So there's exceptions to everything. And VLANs can be 1522 because you have to add in the 4 bytes for the VLAN. And then there's special purpose, like some versions you can do a jumbo frame where you can set it. It can be set above 9,000 bytes. So sometimes you have that. But the maximum size of an IP packet is 5,536, while the network layer packet being transmitted is only 1,500 bytes. So, fragmentation and segmentation are the things that govern this. And so routers examining incoming packets for IPv4, if it's larger than the outgoing interface's MTU, so if it's larger than 1,500, it's going to be able to be fragmented. So the problem with fragmentation is it slows down the network. So really we want to have an MTU that's set for the best performance for the network. TCP tries to avoid fragmentation with the maximum segment size so that it defines the maximum size of that transport layer. So it tries to do that. Legacy networking, so we always talk about things from back in the day. 8023, it was officially called CSMA/CD, Carrier Sense Multiple Access with Collision Detection, and then called Ethernet afterward. So it uses a little bit different layout than the Ethernet 2, but the reason, the meaning behind the name Carrier Sense is just a node on the Ethernet line waiting and listening to transmit data. So it's going to wait until no one else transmits data, and then it'll do that. Then multiple access means there's multiple nodes accessing that network at the same time. And then collision detection is what happens to when multiple nodes or more than one node attempts to transmit at the same time. So there can be a collision. And so if two nodes interfere with each other, we get a collision. And after the collision, that node waits a certain amount of time and then resends. So a collision domain is where all of this happens. Hubs just repeat collision domains, while switches break up, each port on a switch breaks up a collision domain, which is why it's, we don't have as many issues because we've been using switches. And then we'll talk about cable structuring and if a cable is too long, but part of that is with the CSMA/CD. So the reason we talk about CSMA/CD is because you need to know and understand it and how to troubleshoot it for collisions. So we'll talk more about it in upcoming chapters as well. All right, 4.2 is in the next section, and that is everything for section 4.1 in the Network Plus Guide to Networks by Cengage.